Stereochemistry is a very important topic, whether you talk about competitive exam or your general learning of chemistry. So if you belong to any stream of chemistry, whether it is inorganic or organic, stereochemistry is always important. And for organic chemists, it is the one of the most important topic that you should have clear idea. So in this video I will be talking about the introduction of the stereochemistry of organic compounds, and I will make a series of videos on stereochemistry where I will cover from the beginning, that is the point group and symmetry, to the nomenclature, RS nomenclature, and the conformation configuration, to the application of stereochemistry in organic reactions. So welcome to chemistry lover, and let's start today's topic. So this is the introductory video for the stereochemistry, and in this video I will be basically talking about the symmetry elements, the point groups, and and if I get time I will talk about the different projection formulas for representing a particular molecule. So you can see this is the representation of methane. Okay, if you ask anyone that what is the structure of methane, he will say that methane is this kind of structure. Okay, and the same thing I have drawn here, where I represent this carbon as a dot, but this shows that methane is a 2D molecule, and this is actually a problem that we have to represent our molecules in a piece of paper. So we have to represent our 3D molecules in 2D paper, but we should remember always that molecules are not 2D, they are 3D, and so the atoms in the molecules are spread in the space. Okay, so that means actual structure of molecule is 3D, and when a chemist see the methane molecule, he will see this structure, that is two of the hydrogen atoms are on the board and other two, one is above the board and one is below the board. So this is below the board and this is above the board, and this particular formula, projection formula, is called the flying wedge. Okay, FLY, flying wedge. Flying wedge formula. I will later discuss that what are the different projection formulas, but for now you just know that this is the flying wedge formula for representation of 3D organic molecules in 2D sheet. Okay, so these are the case. Now why stereochemistry is so important? So if you study the organic reactions, you will see that for any useful reaction it involves some kind of stereochemistry. Or if you consider the biological system, all the molecules are chiral. What is chiral? Chiral means the molecule has a particular three-dimensional structure and that has a particular arrangement. Okay, I will later discuss what is chirality, but that involves some kind of stereochemistry, and stereochemistry, that's why very important. If you don't represent your stereochemistry, or let's say you write a reaction and no stereochemistry is manifested in your product or in your intermediate, then it has no meaning, right? So stereochemistry is very important when we consider organic reactions, and if you want to study organic reaction, you have to know about stereochemistry, because without stereochemistry you cannot write a single reaction. Okay, so we will discuss, or we will begin our discussion of stereochemistry by first talking about the symmetry and the point group. So symmetry is another very important factor. If you know symmetry or the point group of a particular molecule, you can easily tell about the properties, mostly the physical properties of the molecule. So just knowing the point group and the symmetry elements present in a molecule, you can easily tell about what are the physical properties of that molecule. Okay, so that's why symmetry, knowing about the symmetry of molecule is very important. Now all the symmetry elements of a particular molecule, or not molecule, any substance you take, it will have a certain symmetry elements, right? And all the symmetry elements are classified into two categories. Okay, one is the symmetry of first order, and another one is the symmetry of second kind. Okay, now among the symmetry of the first order, there are two symmetry elements. One is the axis, principal axis of symmetry, and another is the plane of symmetry. Either it may be sigma v or it may be sigma d. Okay, these two fall into the category of symmetry of first order, whereas in the symmetry of second order it belongs like Sn, that is it is one kind of symmetry, and I is the symmetry of second order, which is called point of inversion. We will talk about all the symmetry elements and in which molecule what type of symmetry elements are present, that we will discuss. Okay, so let us first take a very simple molecule, for example BF3. So this is the molecule BF3, and so we are representing this molecule in such a way that this fluorine atom is below the plane or behind the plane, and this fluorine atom is above the board and this fluorine atom is on the board. So that means we are representing it like that. So this is how we are representing this BF3. Now you can see if we label this as 1, 2 and 3, we can have a axis from here on rotation of that axis of 120 degree will give a arrangement like this, same kind of arrangement, but let's say it is rotating in a anti-clockwise manner. So now F2 will go here, F1 will go here, but F3 will go here. So you can see the position of the atoms are changed, but the configuration is same, or the representation of the molecule is same. So that means by rotation of this particular angle, same structure is regenerated, or we can say that it has a symmetry operation. So what is symmetry operation? Symmetry operation is basically such an operation which give you back the same arrangement of the molecule. So here it is a Cn symmetry operation, and now we have to find out this n. So how to find out this n? So this n is equal to 360 degree by this 120 degree. So let's say this is theta. So for any rotation that we consider theta, and overall rotation we know we can maximum rotate by 360 degree. So this is why 360 by 120, so that is equal to 3. So in this case this is C3. So this is called the C3 axis. So you can see in this molecule a C3 axis is present, and you cannot have any other axis which is greater than n value 3. Okay, so this is the highest fold rotation for this BF3 molecule. But you can have other rotation axis, like let's say you can consider a rotation axis from this which passes through this BF bond, and if you rotate it by 180 degree you will get this configuration where you have this F1 fixed, but now this F2 will go here and this F3 will come here. So you can see again same kind of representation is attained. So again this is called a symmetry axis, but in this case you will have n equal to 360 by 180, that is 2. So this is called C2 axis. Okay, so the highest pole rotation axis called the principal axis of rotation, and side by side you can have other axis of rotation, for example in this case C2. And one important thing in this case is that this C2 axis is just perpendicular to this C3 axis. So this is called perpendicular C2, and it is represented as this perpendicular C2. And another thing is noticeable that along all the BF bond you can consider one C2 axis, and that will result total of 3 C2 axis, which is equal to the n value of your principal axis of rotation. So your principal axis is C3 and you are getting 3 perpendicular C2 axis. So this is a relationship that if you have a principal axis of rotation Cn, and at the same time you are having perpendicular C2 axis, then it is for sure that you will have n number of perpendicular C2 axis, not less than n or not greater than n. That can be exemplified by taking another molecule. For example, let's say we take the cyclopentane, right? So this is cyclopentane, although it is not in planar form, we take it as a planar form, or let's say cyclopentane dinyl anion, so which will be in the planar form. So now we can consider a axis which is just passing through the center of this molecule, and that rotation of that axis of 5-fold will generate the same configuration. So that is called C5 axis, right? Now you can also consider, see, this axis you can also consider like this. Okay, so these 3 axes you can consider from here, and another one, these. Okay, so these are like 1, 2, 3, 4. Okay, so 4, and another one is here. Okay, so 5. So you can see these are all C2 axis, because rotation of this axis will give you the same arrangement. Let's say if you rotate along this axis, so what you will get? So let's say you number it as 1, 2, 3, 4, 5, 6, and you are rotating along this axis. So it will give you the same kind of arrangement like this, but here what will change? So 4 will be the same, but here you will have so actually this is 2, 1, 2, 3, 4, 5. So actually this will be 3. So this 3 is fixed. You are rotating along this axis, this particular axis you are rotating. So this will now be 2, this will now be 1, this will now be 5, and this will be 4. So you can see you are generating the same configuration, but the atoms, the position of the atoms are changed. So this is called the C2 axis, and it is noted that in this case the principal axis is C5, and you are getting 5 perpendicular C2 axis. These all are perpendicular C2 axis. So this is a foolproof relationship. If you consider benzene, there you will have C6 axis, and you will also have 6 perpendicular C2 axis. Okay. Now let us take the second kind of symmetry axis, symmetry element, that is plane of symmetry. So what is mean by plane of symmetry? So plane of symmetry is a particular symmetry operation in which you can have a plane along the molecule, maybe along the bond, or maybe along the atom. It is such a plane which bisects the molecule in 2 halves, and that 2 halves will exactly behave as object and mirror image. For example, let's say take the same example of BF3. So this is your BF3 molecule F, this is your another F, and this is your F. So this is F1, F2, F3. Now let's say you consider a plane like this, which is bisecting this BF bond, which is along this BF bond. So now you can see this F3 and this F2, they just behave as one act as object and one act as mirror image of that object. So this plane is called the plane of symmetry, and it is represented as sigma V, right? Now in this molecule you can again imagine that all 3 sigma V are possible along all the BF bond. So 3 sigma V's are possible. But after that, whether let us see that can we have another plane of symmetry? So we can always have whenever we have a planar molecule, we can always have a plane of symmetry that is along the plane of the molecule, which is called molecular plane. So in this case also, so this is your BF3 molecule, and you can always have a plane, along the, which is parallel to the plane, or which is just the molecular plane. So this is another plane, and this is called sigma horizontal. Why? Because you can see the principal axis is this. So this molecular plane is just perpendicular to the principal axis of rotation. So whenever you have a plane which is perpendicular to the principal axis of rotation, that is called sigma H or sigma horizontal. So these are differences. This is called sigma vertical. So any plane which is parallel to your principal axis of rotation. In this case, you can see this is your principal axis of rotation, and all these sigma planes are parallel. That is, they are coincident with this plane of principal axis. So they are called sigma vertical because they have vertical relationship. Whereas in this case, it is horizontal. That is, it is perpendicular, and that's why it is called sigma horizontal. Now, you can consider any molecule and can find that whether that molecule contains sigma V or not. I am not discussing much examples. So after that, I'll talk about the symmetry of the second kind, that is improper axis of rotation. So what is basically improper axis of rotation? So improper axis of rotation is represented by Sn, and which is basically Cn into sigma v. So that is a rotation followed by reflection, rotoreflectory axis. This particular symmetry operation is sometimes called rotoreflectory axis. So for example, let's say we take the ethane molecule in its staggered configuration. Okay, so this is your ethane molecule in its staggered configuration. So first, let's say it is rotated by 180 degree along this, considering the axis along this, and if we rotate it by 180 degree, what we will get? We will get this. Okay, so this thing we will get, because you can see if you just rotate it by 180 degree, this top hydrogen will come to bottom, whether this bottom hydrogen will go to top. So this you will get. Now place a mirror plane along here. So this mirror plane you have to place perpendicular to this CN axis. So in this case it is C2 axis, because it is 180 degree rotation. So which rotation axis you will consider? Your mirror plane should be perpendicular to that. This is one requirement. So now if you place mirror image, what image you will get? So the image you will get like this. Sorry, the image you will get like this. Okay, so this hydrogen, and here again hydrogen, and this hydrogen. Now if you consider this molecule and this molecule, you can see they are exactly the same. In this case also, this hydrogen is above, this hydrogen is above, these two are below, these two are below. In this case also, this is below, these two are above. So by C2 rotation, and after that reflection along a plane which is perpendicular to that C2 axis gives the same arrangement. So this process is called the symmetry of second kind or rotoreflectory axis, and in this case this is S2, because it is basically C2 into sigma v. This is sigma v, so C2 into, or in this case that's just sigma you can say. So C2 into sigma, so that's why it is called S2. So this is called symmetry of second kind, and it is a result of rotation followed by reflection. Okay. Now the last kind of symmetry element is the point of inversion. So what is point of inversion? Let's say you have benzene. You have benzene, and you consider at the middle of benzene this point. Now if you travel from this point to here, and if you travel this point to here, you can see on the opposite two directions same distance are traveled. Or you can say let's say you travel this side and this side, exactly the same, so same distance are traveled. Or let's say if you have other molecule like say a square. So in square also, if you, so this is basically cyclobutane in its planar form, so which is we consider it to be perfectly a square. So then also you can see, if we travel from this point to here, and if we travel from this point to here, same distance has traveled. So if this relation is satisfied, that we can imagine a point within a molecule, and if we travel from that point to one direction and then to the opposite direction, and same distance is traveled, then this molecule is said to have a point of inversion. You can see, if you consider this cyclopentane, then you can see there is no such point of inversion, because in this case traveling across the a particular direction, and the travel along the opposite direction will give you different distance. So not all molecules contain this particular symmetry. Some of the molecules like benzene, which has a perfect shape, or which has a very high degree of symmetry, that contains this plane of symmetry. Okay, so this is also a symmetry of second kind. Now there is a nice relationship between S2 and I. So you can have S4 or S6 like that. So it is not like that S is only S2. It is general Sn, and n can have any value depending on the value of C. So but within a molecule, if it has S2, then it is for sure that the molecule will have I. Now we can prove it by considering any example, but For example, the which I just discussed, that in the staggered configuration of your ethane, like this. So you can see, if you consider a plane at the middle, a point at the middle like this. So now if you travel along this and travel along this, you can see same distance are traveled and same atom is achieved. So this molecule has point group symmetry, point of inversion I, and at the same time I just shown that it has S2 axis. Okay, now I will prove it in general. Okay, so for that we have to consider a Cartesian coordinate system like that. Okay, so this is a Cartesian coordinate system where you have this as the y-axis, this as x-axis, and let's say this is z-axis. Okay, now let us take a point here. So this point, let's say it has a coordinate of x, y, and z. Now let's say we rotate this point along
y-axis by 180 degree.
So basically a C2 operation. So that will generate a point here. Now this point will have a configuration of minus x, y, and z. Minus x because it is at the negative coordinate of x, but it is at the positive of y and z. Now let's say we place a mirror plane along this, because we are rotating along y-axis. So we have to place the mirror plane which is perpendicular to this y-axis, right? So this mirror plane will generate a mirror image of this point here, and that will have a coordinate of minus x, minus y, and minus z. Okay, now that means by this operation we get a point minus x, minus y, minus z from starting from x, y, z. So this operation is C2 into sigma. So this is basically S2 operation, but at the same time you can see a point which is x, y, z, and a point which is minus x, minus y, minus z. These two are basically the inversion point of one another. So this is also an inversion operation. So you can see the same operation, inversion and C2 will give same result. So this is a relationship between C2. So if you find point of inversion for a molecule, it is guaranteed that the molecule will have S2, right? So this one. Now these are all the point groups, and from books you can practice any molecule or any substance you can take and try to find out that what are the symmetry elements present in this. Now based on the symmetry elements we can classify the molecules in point groups, and that thing I will discuss. What are the rules for classification of molecules in a particular point group. So there is a hierarchy for classification of molecules in point groups, and that starts from the first point is, let's say you have a molecule which has only Cn axis. Sorry, let's say a molecule which has only Cn axis and the n value is 1. That is, the molecule has only C1 axis. For example, let's say take any substance which has no symmetry, like a piece of rock, right, which has no symmetry. So that will have only C1, because in every element there is C1 axis, right? So now this molecule will belong to the C1 point group. So that point group is called C1. Okay. After that, let's say you have a molecule which has a Cn proper axis of rotation, but it doesn't have any other symmetry. For example, let's say take any molecule which has a C3 axis of rotation. I am not representing the real example, but let's say you have a molecule which has only C3 axis and no symmetry plane, no point of inversion, nothing. So then the molecule will have the point group of Cn. Okay. After that, let's say you have a molecule which has only a plane of symmetry and nothing else, no axis of rotation, no S, no nothing, only sigma. So then the point group will be Cs. Okay. Then another situation may arise when you have only point of inversion. That is, you can have S2 and point of inversion and nothing else, no proper axis of symmetry, no sigma plane. So then the molecule will have a point group of C5. Okay, so these are very uncommon point groups. Like you will have one, most of the molecule will contain more than one symmetry elements. So these are special cases where you have only one kind of symmetry. and these are very less important in terms of our organic chemistry point of view. Okay, so the main point group starts from when, let's say, you have a molecule which has CN axis and at the same time it has a sigma plane like sigma V. So then the point group will be CNV. For example, let's say you have a molecule BF3, not BF3, let's say you have a molecule like ammonia. Okay, so let's say you have ammonia molecule, and this molecule you can see a C3 axis is there, rotation of C3 axis, and also along each NH bond there is a sigma V plane. So ammonia molecule falls into the category CNV. So in this case CNV means C3V. Okay, but if your molecule contains sigma 8, for example your BF3 molecule also has the sigma V, but at the same time it has sigma H also, which is the plane of the molecule. So if with the along with the Cn and sigma V, if it has CH also, then the point group will be CNH, right? So for BF3 molecule the point group is C3H. Okay, now the next point is, let's say it is not complete, for BF3 it is not complete. Let's say in your molecule you have a CN axis and your sigma V or sigma H, that doesn't matter, and also along with that you have perpendicular C2 axis. For example, in this case you have the perpendicular C2 axis. We have already shown that we have perpendicular C2 axis. So at that point your sigma V is called sigma D. Okay, and the point group is changed from C to D. That is, let's say for BF3 in this case, we will represent the point group of BF3 not C3H but D3H, because it has also the perpendicular C2 axis, right? Now let's say in a case where you have C2 axis but you don't have sigma H, then what will happen? Your point group will change from CNV to DND. So whenever you have a sigma plane but you also have C2 perpendicular C2 axis, then that sigma V is called sigma D. So sigma V means sigma vertical, but just the presence of C2 means you have a dihedral angle. So this C2 are present means these planes which are present in your molecule, they form a dihedral angle, and that's why it is called sigma D. So that's why we called sigma D and not sigma V. So your point group will change from CNV to DND, right? So in this case also as H is present, so this is DNH. So these are the main features of classification of molecules in point group. So in the next video I will discuss about what are the importance of point group, and what is symmetry number, what is its application, and later I will discuss about the configuration and conformation of the molecules. So if you are new in this channel, then subscribe my channel, and if you like this video, then give a thumbs up and share this video with your friends, and thank you for watching.